In the last mini lesson, we saw an example of making a free body diagram and applying Newton's second law to an object in equilibrium. In this mini lesson, we work through another example, but now involving an object that is accelerating. Another new feature in this example is that we'll see how it is sometimes convenient to use a coordinate system that's tilted relative to horizontal. First, however, let's briefly review the procedure for drawing free body diagrams. A free body diagram is the starting point for virtually all problems involving applications of Newton's second law. To draw a free body diagram, start by selecting an object of interest from the given problem. Then identify all of the forces acting on that object, including forces exerted by other objects in the problem, or by external agents such as Earth's gravity. Next, draw a coordinate system, bearing in mind that the most convenient orientation of the axes may not be the traditional horizontal and vertical axes. Represent the object by a big dot at the origin, and then draw in and label all of the force vectors you'd identified earlier. Finally, to the side, draw and label the net force vector, which is the vector sum of all the other force vectors. Now on to our example. A 12-meter frictionless ramp makes an angle of 16 degrees with the floor. A 45-kilogram crate sits at rest at the foot of the ramp. When a steady, horizontal pushing force is applied to the crate, it slides up the ramp, reaching the top in 6.0 seconds. Determine A, the pushing force, F sub P, applied to the crate, and B, the normal force, F sub N, of the ramp on the crate. As always, we start by sketching the scenario presented in the problem. Let me emphasize that this is not a free body diagram. A free body diagram abstracts out the superfluous details to make it easier to focus on the details that will let us solve the problem. We start with a sketch, however, so that we can connect the abstractions of the free body diagram to the specific features of the problem, in this case that a crate is being pushed up a ramp. Now that we have a sketch, let's begin to build our free body diagram. The first step is to select an object of interest. In this problem, there really is only one object of interest, the crate. Next, we identify all of the forces acting on the object. Obviously, there's the horizontal pushing force we're told about in the problem. I've drawn an arrow representing this force vector on the sketch, but this is just to organize my thinking. It still isn't a free body diagram. The ramp is exerting a normal force on the bottom of the crate, where the two are in contact. Remember that a normal force is normal or perpendicular to the surface of contact between two objects. In this case, that means the normal force is perpendicular to the ramp. And finally, the Earth is exerting a gravitational pull on the crate. That's just its weight, mg. Now that we've identified all the forces acting on the crate, we can begin drawing. We start by drawing coordinate axes, placing a dot representing the object at the origin, like so. However, is the standard orientation of the axes the most useful for this problem? Since the object is constrained only to move along the ramp, it makes sense to have one of the coordinate axes parallel to the ramp. That way, the acceleration vector needn't be resolved into components. So we rotate the axes counterclockwise by 16 degrees so that the x-axis points up along the ramp and the y-axis points perpendicular to the surface. Next, we draw in and label the force vectors, with tails on the dot representing the object. First, there's the horizontal pushing force. Then the normal force, which, by our choice of coordinate axes, points along the y-axis. and finally the object's weight, which points straight down. The last step is to draw in and label the net force vector slightly off to the side. Note that we expect it to point up the ramp because the object's acceleration points that way, and net force and acceleration always point in the same direction. Okay, now we have a complete free body diagram for the crate. We now use this diagram to help us write down the x and y component equations for Newton's second law as applied to this problem. Simple geometry tells us that f sub p makes a 16-degree angle with the positive x-axis, and that f sub w makes an angle of 16 degrees with the negative y-axis. We're now ready to resolve all of the force vectors into x and y components. The x component of f sub p is adjacent to the 16-degree angle, so it is f sub p times cosine of 16 degrees. And similarly, the y component is opposite to the 16-degree angle, so it is negative f sub p times sine of 16 degrees. Why the minus sign? Well, because the y component of the s sub p vector points in the negative y direction. The normal force points entirely in the plus y direction. So its x component is 0, and its y component is f sub n, the magnitude of the f sub n vector. Finally, the x component of the weight vector f sub w is opposite to the 16-degree angle. So it is given by negative mg sine 16 degrees, with the minus sign indicating that this component actually points in the negative x direction. Similarly, the y component is adjacent to the 16-degree angle, and therefore is minus mg cosine 16 degrees. Again, the minus sign reflects the direction this component points. Now we apply Newton's second law. Since it's a vector equation, there are two component equations. The sum of the x components of the forces equals the mass times the x component of the acceleration. In this case, that yields f sub p cosine 16 degrees minus mg sine 16 degrees equals ma, where a is the as yet unknown acceleration of the crate up the ramp. We also get a y component equation. The sum of the y components of the forces equals the mass times the y component of the acceleration. But since the crate is stationary in the y direction, a sub y is equal to 0. So we end up with f sub n minus f sub p sine 16 degrees minus mg cosine 16 degrees equals 0. There are two unknowns in the problem, f sub p, the magnitude of the pushing force, and f sub n, the magnitude of the normal force. So we can now solve the first equation for f sub p and the second equation for f sub n, like so. We know m and g, so if we only knew a, we could evaluate the first equation to get f sub p. And once we have f sub p, we can plug it into the second equation to determine f sub n. But what is the acceleration? Well, we're not told that specifically in the problem, but we are given enough information to deduce it. Because the pushing force is steady, the acceleration of the crate up the ramp will be constant. Therefore, we can use constant acceleration kinematics to determine a. We are told that the ramp is 12 meters long, that the crate starts from rest, and that it takes 6 seconds to go from the bottom to the top of the ramp. The first constant acceleration equation tells us that delta x is equal to v naught times delta t plus 1/2 times A times delta t squared. Since the crate starts from rest, V0 equals 0, and solving for A gives A equals 2 delta x divided by delta t squared. And plugging in numbers, we find that the acceleration of the crate is 0.667 meters per second squared. Now that we have A, we plug it, along with m and g, into the equation for f sub p, and find that f sub p is equal to 157.7 newtons. Then we plug that value into the equation for f sub n, and find f sub n equals 467.4 newtons. Now we can answer the questions in the problem. The pushing force on the crate is 158 newtons, and the normal force of the ramp on the crate is 467 newtons.